What's up, everybody? The Hybrid Guy here, and today I have a great episode for you on the channel. What I'm going to do is actually dive into what all my secrets are with repairing hybrid batteries. We're going to look at how to repair them the right way, what to test for, what to look for, everything that you need to know on how to properly repair and fix a nickel metal hydride hybrid battery. Now, the great thing about this is the ideas and the concepts that we're going to be using here today are pretty standard across nickel metal hydride batteries. So if you have a Honda, if you have a Ford, if you have a Toyota like we've got here, a Toyota battery, this is out of a Toyota Camry, all of these principles are going to mean pretty much the same thing. So that's where we're going to go with this today. So let's dive in and get started. All right, so one of the very first things that I want to talk about is all the different myths that are floating around on places like Prius chat and all over the internet, you know, oh, my great grandpa who invented nickel metal hydride said this type of stuff, right? Because there are so many rumors. Now, rumor number one is that if my battery here has one bad module, right, that I can just replace this module, put the whole pack together, not recondition it, and put it back in the car and it will be okay. Well, maybe it might. But the thing is with all the other things that we're going to look at today, that'll help you understand why just replacing a module or two in a pack is not the most effective thing. Because what ends up happening is you could have one dead module and you put a new one in, and if that module performs better than the other ones, the pack is going to be out of balance. So you're going to hear me use several terms today: balance, recondition, charge, discharge, and all of those have significant meaning in ensuring that we rebuild a battery pack back to as close to new as we possibly can. So let's start with what some of these terms mean so you can get a better understanding of how and why it's important to know them when rebuilding a hybrid battery pack. Kind of the overview process of what we're going to be doing here, I'll give you that, is I measure several different things on these battery modules. The first thing that I do, and you may not see me do this, I haven't decided if I'm going to do it on or off camera, is I strip all the nuts and the bus bars off. And I look at them for corrosion. Now, if they've got a lot of corrosion, I'm going to look at the studs that are on the modules and see if they've been leaking. If they have been leaking, I'm going to try to find a good module to replace that one because I don't want to have corrosion issues. The second thing that I do that people debate about all the time is nickel-plated bus bars and stainless nuts. Now, there are some people out there who claim to be electrical or mechanical engineers and they say, oh, well, nickel inhibits electron flow. We're talking about nickel plated. We're not talking about solid nickel. And the ultra microscopic thin layer of nickel that is on the new bus bars that I have for this does not affect the flow or transfer of electrons. In fact, it's so minimal, it's just totally negligible that you would even have a resistance in that. And so I upgrade everything because what I'm trying to avoid is getting a bunch of garbage like this corrosion on the nuts and on the bus bar there, because I want to have maximum electron flow. And with nickel plated bus bars, that is one way that you can help prevent a severe amount of corrosion buildup. So in case you're reusing modules and that one ends up leaking later on down the road, you're not going to get a ton of corrosion on there because that nickel inhibits a lot of this corrosion growth that we are seeing on some of these bus bars. So what I do when I strip all of these bus bars and nuts and everything off from both sides of the battery is then I take what's called a resting voltage check. And I go through and I test each module, each one of these I test and see what their resting voltage is. That way it gives me kind of a baseline to know how well this battery has been at sitting, how well it's performed at sitting. And why is that important? Well, if I have a module, right, that's been sitting, let's just pick this one out randomly. If this one's been sitting and that one's been sitting, and this one is at 5 volts and that one's at 7.5 volts, I can start to assume that this module may be bad, that it may not recover during a reconditioning process. And so I want to note that in my notes, right? Because I keep a notebook, which is right there. I keep a notebook of all these different things. So initially I do a resting voltage and I note that down what all of them are. Then from there, I do another process. The second process that I do, and we will do this, is I use these Prolong Pro module testers. And what they do for me is several different things. But the next one, which I do, is I do what's called an internal resistance test. And what that is it measures the amount of resistance in milliohms in each module. And why is that important? Well, on a really good working battery module, we want to have the smallest amount of resistance as possible. And the reason that is because the more resistance we have, the harder it makes it for the electrons to move inside of the battery modules. And when that occurs, if we have high resistance in a module and the electrons can't flow, they need to find a way out. And I've had this happen to me before, where I've gone and rescued a hybrid. I rescued a Prius recently that had a bad module in it, right? And what happened is, because the modules couldn't, or the electrons couldn't flow, they tried to find a way out, and I ended up exploding a module because it was so bad, it was so corrupt that the electrons wanted out that bad. So they blew the top off the module. And so every time I recondition or work with the battery, I always test for internal resistance. Now, the higher the resistance, the less electron flow, the less likely that you're going to have a battery that's going to last a really long time. But you can find modules with higher resistances that will balance out and work together. I recently put together a battery for a Toyota Prius that had fairly high resistances, but I reconditioned it anyway just to see how it would work out, and I actually just pulled it out of the car. It's right over here, and guess what? Nothing exploded, everything worked out well, and it actually will probably work for, well, at least a couple more years. So it is possible to use modules of higher resistance. My suggestion to you, if you're new to this, if it feels suspicious, it probably is. So don't think that you can just dive into this and know everything you possibly can about reconditioning batteries just from watching this video. I would tell you definitely to do some more research, but I will say that this will give you as much detail as I possibly can for the tools that I am using. So another thing that I measure is when these Prolong Pro module testers measure the resistance, they also do perform another function called voltage drop. Essentially what that is the little computer in here says, okay, the battery module started out at 7.5 volts, and we loaded it. We put a huge amperage load on it, anywhere from about 40 to 50 amps for about 30 seconds. And what that does is it shows how many volts it started at and how many volts it ended at, and that was our voltage drop. And the reason that that is super important when repairing a battery is because the higher the voltage drop over time, the weaker the module it is. Again, this goes back to why you can't just randomly throw in a module that has 7.5 or 8 volts or whatever and expect it to function. You need to test it under a load in order for you to know if that module is going to hold up when it's in the car. Because these modules, this whole battery, what it does constantly when it's in a car is it gets charged and discharged, charged and discharged. And it gets loaded every time you step on the accelerator. Energy from this battery is going to flow to the motor generators and it's going to help propel you down the road. If there is not enough available energy, when this battery starts to get depleted, guess what happens to your car? Check engine light, poor performance, poor fuel economy, all of those things are going to happen if you haven't taken the time to understand that voltage drop means if you have severe voltage drop of a volt or more, right, you're probably going to have a battery that's not going to perform the way that you want it to. And it could be a lot of time wasted. So the lower the voltage drop, the better. Typically, I try not to use anything over 1 volt of voltage drop. But again, I did an experiment with that battery over there where some of the modules had a little bit over 1 volt of voltage drop. And I did that to see how far I could really push a nickel pack to work in conditions. And it was really because I don't have a ton of good modules, and I've reserved all my good modules to ensure that this battery pack works. And the other battery pack that I've been working on was already okay. But when you have a lot of modules that need, essentially, here's what you need to know. What you need to know is if you have high voltage drop, don't necessarily discard that module, but do some other forms of testing. If you have 28 modules or 34 modules that all have 1 volt of voltage drop or less, they can probably still all work. You're gonna, of course, want to compare notes with how well the internal resistance readings are, after you do those tests as well. But they aren't necessarily bad. They may just not perform exactly the way that you want them to. So what I like to look for is low internal resistance, low voltage drop, and those are my 2 main big things. And of course, resting voltage as well. Now, I want to show you some notes of a couple batteries that I've rebuilt recently. This one, it had been previously rebuilt by Green Tech, and as you can see, taking a look at the internal resistances, they were all pretty high. They were way up there. And the voltage drops, pretty much everything was over a volt of voltage drop. But what was really cool about this battery, and this kind of helped prove my theory, is that even though these looked really terrible, I reconditioned this pack, I put it back in the car, and I sent the car down the road, and that customer's still living on very happily with how well this battery is performing. Is it perfect? No, but does it work? Yes, and it does give those battery modules and that whole battery and that whole car another life. As compared to notes over here. This was a spare battery that I was actually building for a friend of mine. You can see I measured my resting voltage, my internal resistance, and my voltage drop. If you look at these particular modules, everything was under 1 volt. And even though the internal resistances were a little higher than I wanted, this was before I conditioned, so this was pre-conditioning. And what ended up happening is all these resistances fell below into a usable threshold of what I would really like to see. Now, if you are unfamiliar with what reconditioning does, let me explain that to you in just a moment. I want to take a moment and talk about what the reconditioning process actually does for your battery. When the modules get some wear, they get some time, they get some age on them, they start to build up what are called dendrites. Dendrites are these tiny little microscopic things that form on the internal plates of the battery. And when that happens, a dendrite is like a wall. And when an electron tries to flow through a dendrite, it doesn't work. Now these dendrites web like a big kind of spider web looking thing across the plates, and so as they grow and they build, they reduce the overall capacity of the battery, right? And then again, they inhibit that electron flow. When we inhibit electron flow, what happens is the internal resistance goes up, right? So the higher the internal resistance, the less electron flow we have, and also the less capacity that we have. Let's kind of back up there for just a moment, because some of those terms we really want to get familiar with. What is capacity? Well, let's say that I have a 5-gallon bucket here. The capacity of that 5-gallon bucket is 5 gallons, right? If I fill it halfway up with sand or rocks or debris or whatever, right? Now I have diminished capacity, which means if I go to fill that with water, I only have maybe 2.5 or 2 gallons or maybe 3 gallons that I can actually fill, because the rest of that debris is taking up how much space or capacity, all right, inside that bucket. And a very similar thing happens when we get dendrite formation inside of our nickel metal hydride battery modules. As those dendrites form, they decrease the amount of capacity that they have, and they, of course, increase the resistance. So that is why I test for internal resistance, that is why I test for voltage drop, and that is why I look to see how old these modules really are, because age does play a factor as well. But if you can have a really old module and have it perform well, that's totally fine. I like to think of modules as players on a soccer team. Pick your favorite soccer team. And if these modules are all balanced and working together, that team's going to win, which means your car is going to go down the road. Well, let's say that we get a bad module, right? Somebody gets injured, or we've got to pull that battery module out for whatever reason, that player's down. Well, if we happen to have a brand new module and we stuff it in there, right, that module is going to outperform all the other ones that have learned how to play with each other, right? They've been in balance. They know what that is. So what we have to do when we rebuild a battery pack is we have to find players that work with each other. That's why my theory that I have here of, even though some of the modules that I've used have had higher resistances or voltage drops that I didn't really like, once they were reconditioned and balanced, that pack was able to function again. But there's another hidden thing in here that I want to talk to you about, what reconditioning actually does. When we recondition a battery, think of it as like a shovel or your hand or something going down into the bucket and scooping out part of that sand or rocks or debris that's in the bucket and increasing the capacity of the bucket, right? So when we fully charge and balance and we discharge and charge and discharge and do all of that, what we're doing is we're helping to restore lost capacity inside of these battery modules. That is why the reconditioning process actually works, is because sometimes we can get these modules to recover. So, in short, reconditioning through a series of charging and discharging will help restore capacity. When we are on our final charge, we balance the battery, which means we charge it all the way up, and then all of these modules become balanced. And having a balanced battery is very critical to having the team, right, perform well so your car can make it safely down the road. So something that I always do before I start tearing into any battery pack is I get out my notebook and I write down how many modules there are. Then I write down RV, which stands for resting voltage, IR, which stands for internal resistance, and VD, which stands for voltage drop. Right, so I've got that listed out here, and I've listed my modules as C1 through C34. And what I'll do is I'll take my permanent marker, and I'm going to label each one of these as C1 through C34. And then what I'll do from there is pull off all these nuts and bus bars on both sides and start to do my testing. Now with my testing, what I like to use, again, I've showed you what I'm going to use for doing the internal resistance testing and the voltage drop, but I also use my very trusty Fluke 88.5. One of the reasons I like Fluke is because they are incredibly durable. They're an industry standard, and yes, this cost me a lot of money, but I know that I'm going to get accurate results with my Fluke. I check every other thing that I use against this because I consider this to be my gold standard of testing right here. But there's some things that this can't do that I need these for, but whatever I can do, I check with my Fluke. That means voltage always gets measured with my Fluke, and anything else that I can do I test with this guy right here. So now what I'm going to do is label my batteries, and then I'm going to just dive in and start pulling off all the hardware so I can start doing my voltage drop, or not my voltage drop, just my resting voltage testing on all these modules and get that. That I wanted to show you is while I was measuring this, if you notice I kept the leads on the same side, which means I used the same lead on one side as I did the other. And yes, the modules change polarities from side to side, but why did I do that? Let me show you. The reason that I did that is because what a digital voltmeter is doing is voltage is pressure, and what it's doing is it's measuring the pressure. So if I have these hooked up in the wrong way, it's just going to say that I have them, I'm looking at things from an opposite view. If I have them hooked up the right way, they're going to show me that I don't have that minus sign there, and I have things hooked up from the right view. It's still measuring the pressure. It's okay. I just do this for speed so I can get through all of my results as quickly as possible. What I want to do now is just look at the results of this quick resting voltage test and show you why this is really important. If you begin to look here, right, we can see that by the time we hit C7, C14, C15, C17, C21, we have some modules here that are under this 7 volt. Now, why is that? Well, those modules could actually be the ones that are going to give me the most trouble. Is it always that way? Not necessarily, because I've seen modules with really high voltages fail. Some of that are in like the 8 volt range too. But these ones are definitely suspect because this battery has done a couple of things. One, it's been sitting. So I know that if it had a surface charge on it, which is a surface charge is basically a charge that is on a battery after it's been recently charged. But this battery's been sitting for about 2 weeks now, and so for it to have any surface charge is probably not realistic. And so I know that 7, 14, 15, 21, and 17 there, all of those are suspect modules. That's why what is really critical now is I do this internal resistance test to see how they're all going to perform. I have a suspicion that these ones that are at the 6 mark are going to probably fail that internal resistance test, but as I get everything hooked up and start doing this, I'm going to be using both of these to do this as quickly as possible, just because there's a lot of modules on here, and I want to make sure I have some time left over in my day. I'm going to test these and get all the internal resistances, and then we'll come back and take a second look. So what I've got right now is I've got my first and my last one hooked up, and what my plan is to do with that is to bring and meet up in the middle. So I'm going to utilize both of these. I'm going to not do this on camera just because it's kind of a tedious process, and there's not really, you're going to learn a whole lot from here other than me swapping the leads as I go back and forth down the rows. So I'm going to hit the pause on the record here, but that is the process that I'm doing. This will measure my voltage drop and my internal resistance, and then we'll take a look at the readings after I get this done. Okay, so I've got all of my testing done, and I want to go over these results. Let me zoom in here just a little bit so we can get better reading on those. Now, you'll notice I've got some marked fail in here, and then I've got all the internal resistances, voltage drops, everything. Now, you'll notice like on my C7 here, it was a no pass fail, but we come down to like C16, and even though it measured at 7.46 volts, it failed. Now, I have a theory on this, and same reason why like 21 and 22, if you look at these, you see that 22 has a very high internal resistance and a big voltage drop. If it pairs with a module that is faulty, this module is working overtime because they're connected. So this module could have been really overworked, which is why we're seeing it have such a high voltage drop and such high internal resistance, because this one had failed. Now, again, if you come up to C18 and C17, which, they're buddies because these are all ranked together, these ones, right? All these, and you can just count them by 2. Those are your blocks, right? If you come into that block and then you come into this block, even though this one measured here, it still failed. And it probably failed because, well, a couple reasons. One, it's more towards the center of the pack, so you're going to see the most heat there. And then also, this other one here in C15 was a failure and probably drug this one down. And probably the same thing happened here as well. Now, what's interesting, if we go up to C13, this one initially failed on me, but I tried something different just to see like kind of really a baseline of where it was at. Now, when the module testers, when they do not see that voltage is high enough, it kicks an error code and says voltage is too low, charge and try again. So I charged it. I charged it up over 8 volts, and then I redid the test. And it actually gave me a result of 36.4 milliohms of internal resistance, which is really high, and then 1.5 volts of voltage drop. I'm going to count this module as a fail because it failed initially, and it's probably not going to recondition to where I want to have that module back in my pack. Now, how many modules do I need to fix this pack? If I'm really picky, I'm going to keep everything under 1 volt, right? So I'm probably going to replace this one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 modules. So I need to come up with 12 modules, which I do have, by the way, that will take place, give us lower resistance. And I might leave this one in because the IR is 22.8, which is pretty on point with the rest of these, and it's really just right there at 1. This one, and it squirts on the outer side of the pack too, so it's over here. That one will probably recondition okay, and I know that because of the other pack that I did, the other 2 packs that I did that had higher internal resistances and some higher voltage drops reconditioned okay, and they're performing all right. But there's still a lot of modules in here that I do need to replace that just aren't working, and it's usually right here in this center section, which is very common on Toyota batteries because you get the most heat buildup in the middle of the pack. So what I'm going to do now is go and find myself all the modules that I need, and then I'm going to pull this pack apart and put the new modules in place of this, and then we will go from that point. Something else that I forgot to mention. Now, earlier I talked about corrosion. Now, C25 over in my book passed and should recondition, but if you look right here, you can see that there's some corrosion building around this. What I'm going to do is I'm going to wire brush that off, and then I'm going to seal it with either some dielectric grease or some silicone to help it keep from creeping out, because I want to make sure that this doesn't keep happening. So just so you're aware, if a module does pass, check the terminals and make sure that they aren't leaking. If they are, clean them, seal them, and then recondition it, and they should work out just fine for you. Okay, I have now identified out of my stock, I've got 10 good modules that fit the resistance and voltage drop characteristics of the good modules in here. So what I'm going to do now is pull apart the pack, and I'm going to look at what I've got annotated in my notebook and here, and I'm going to swap out the ones that have failed or are not good. I'm going to put them down in the junk stack, and then I'm going to take these ones and put them in. Now, what I also do with some of these that have, like this one that's 102 and this one up here that's 1, I'm going to make sure those stay on the outer side of the pack where it's coolest. that one's gonna go, that one's gonna stay, and this one's gonna stay. And the reason those ones are gonna stay is because they're really on the edge. I think they're gonna recondition okay, and based on what I saw rebuilding that pack over there, I believe that we can make this pack perform really well, even despite those numbers, because realistically their internal resistances aren't so bad that I'm really worried about it. 23, you know, and 22, and that's pretty much kind of where, if you look at the rest of the numbers, you know, we're right in those ranges anyway. So I'm gonna swap in those now with this. This is a tedious process if you've never done it before. I have to unbolt all of the little 8 or 6 millimeter bolts that are on the underside of that on both sides, and then I've got to pull all of that apart. So I'm gonna do that off camera. It's not something that needs to be seen. If I feel that there's something important that will help you rebuild your pack better, I certainly will tune into that. If you're doing this process, but you're doing it on a different vehicle, if you're doing it on a Ford, if you're doing it on a Honda, of course the process is going to be different. You know, later on when I get my hands on some of those vehicles and I can rebuild those packs, I certainly will. But for now, you know, be as attentive to detail as you can. How did it come apart? What came apart? Did I mark it? Do I know where it went? Make yourself a breadcrumb trail. That way you have an idea of how it came apart, so you know how to put it back together. So I want to give a quick update on where I'm at. I've got the battery reassembled. I've got the new nickel-plated bus bars on there with the stainless nuts. I've cleaned off any corrosion that I could find. You can kind of see down here a little bit on 25, and then again on 19 over here where I've put some silicone around that seal of the module. Where I did that was right, let's see if I can get a good shot for you here. Right where that split is between the metal and the plastic part, that's where I put the silicone. Then I made sure to have that surface 100% clean so we can have contact, so we can have good electron flow. So I've got everything done on both sides here. It's all nice, corrosion free. Now what I get to do, this is one of my favorite things, and I bought this specifically for doing this, because with used modules, potentially leaky modules, you want to be very careful how much you tighten these nuts. So I jumped onto Tecton's website. I really like their stuff. I got a nice inch-pound torque wrench to 48 inch-pounds. I'm going to torque all of these nuts on both sides so I know that they are perfect, and that way we're not going to have any problems with over-tightening or anything like that. And once that is done, then we're going to get this set up to get on its reconditioning cycle, because we are right there ready to go. So I've got my main disconnect hooked up over here. I've got, yeah, everything is on there and ready to go. So I'm excited to get these nuts torqued down and then get this on its first upcharge. Okay, we've got everything hooked up. All the bus bars and everything are torqued down. And we now have it on our first upcharge. This is why I check everything with my fluke meters, because this has 250.4 volts, and over here on my Prolong it shows me 249. Now, is 1 volt a massive discrepancy? No, it's not, but I also don't get to see the tenths of volts that I'm at, right? Because that does make a big difference to know if I'm actually charging or not charging. So what I need to do from here is I'm going to put a fan on top. I didn't put the fan on immediately simply because it makes a lot of noise, and I wanted to be able to have everyone hear what it was that I was talking about. But I need to get a fan on here so we can push air through the battery, keep it cool. This is going to go on until the voltage stops rising. I've got to look on the Hybrid Automotive website and read again really quickly what voltage I need to be at for it to go into balance mode. Because the way that I do my reconditioning and balancing is I let it get to its rising voltage, and then there's a voltage, and it's on this chart on hybridautomotive.com, where the battery then goes into a a balance mode. So I will do a balance, then a discharge, then a charge and balance and discharge. And I do that, and I've had the best results doing it that way. It does take the most time. So if you're very time conscious, you may want to consider not doing that, but all of that's laid out on Hydride Automotive's website. So real quick, just to give you an update, if you cannot find the Hydride Automotive website and find the chart and table, it's right here. So we're looking at the 06 to 2015 Camry. Number of cells that we have is 204. Normal operating range is between 245 and 286 volts, and then peak voltage is up to 292. That is the charge table. So what we are going to do now is when we hit 286 volts, that's going to end our filling phase. And then what's going to happen is we're going to push for 4 to 6 hours after it hits this number to then get it into the balancing part of that phase. So that's what I'm doing right now. So our magic number right now is 286, and then once we hit that, we'll go for an additional 4 to 6 hours to let that balance, and then we will start on our first discharge. So we've got the battery completely reconditioned at this point. I'm going to be reassembling the battery, getting everything back together, but everything has been reconditioned. What that process is it's a charge, a discharge, a charge, a discharge, a charge, a discharge, and then a final charge and balance. What I do for maximum results is every time I charge, I let that charger go for an additional 4 to 6 hours to help balance the modules, to really get them exercised up to their highest point to where they'll break dendrite formation inside each of the cells and help restore lost capacity. Now, this process that I'm doing is repeatable for just about any nickel metal hydride module that you come in contact with. The stick style on Hondas, the other module style that you see in Fords or GMs, you can do this same process, and there is equipment out there that you can get. With Toyota being one of the largest manufacturers, actually the largest manufacturer of hybrid cars and vehicles on the road, equipment's a lot easier to find for the Toyotas, and that's why I've kind of drifted into the Toyota world with hybrids, specifically because there's so much available material as far as tooling and resources to really help get these batteries back into a condition where they can go in the car and put the car back on the road in a good operating condition. So from here, what we're going to do is I'm just going to put everything back on this battery, get it all buttoned up, and then I'm going to put it in the car, and we will do a final inspection and take the car for a drive to see how well this battery has come back to life. Okay, so the battery's in the Camry. I went and took it for a drive, and I went and gathered some data off Dr. Prius. And I wish I would have done this before. I didn't think about it. I was just, excited to get the battery pulled out, and I needed to capture the data before. But if you look, you can see that we have no delta SOC. We have a very balanced battery. If you look at the voltage different PID there, you can see that we have very, very little voltage difference between the modules. And then what I did, we'll skip ahead here a bit, and you can see that I went out and really put the throttle down and loaded this thing up. The second load run that I did it over 10 seconds of heavy acceleration. And what this will do is it will allow you to see how well the battery holds up under a significant load. As you can see, we kept no delta SOC. Our voltage difference stayed incredibly minimal. I don't like to look at the bar graphs on Dr. Prius so much because they're programmed to like really swing hard there. But really what I look at is the voltage difference in that delta SOC. And then I can feel how the car reacts. The car had great acceleration, had a lot of power to it, and I know that this battery is working wonderfully. You can also see each of the internal resistances on the modules. Some of them are at 23, 24 milliohms of resistance. Again, they're a little higher than stock, but they're not so high that this battery can't, give another few years of life to the car, right? And that's really the point, is can we save it? Yes. This is the process that I do that makes it so it's possible to get these cars back out on the road again. This process has come from building multiple batteries, trial and error, and the process that I've shown you on this video today is, in my opinion, the most tried and true method that you can do. If you have a process that you do and it works for you, great. This method works for me. I'm not bashing on anybody else's process. I'm just saying this is how I do it. I get a good, consistent result every time. So if you like it, give me a thumbs up, hit that subscribe button, share this with a buddy or somebody that may need a little bit of battery help. And as always, feel free to reach out to me. Thank you so much for being here, and we'll see you in the next episode.